What if a language model didn't type words one by one, but produced an entire paragraph as the output? That's Mercury, a diffusion-based language model that generates full paragraphs in parallel. It brings big speedups over classic next token LLMs, especially for coding. Welcome to AI Club Pro, where we make AI concepts feel like everyday ideas. Today, we'll cover two things: the architecture that lets Mercury generate whole paragraphs at a time, and the speedups you can expect from this approach. Mercury achieves paragraph level generation by using a diffusion process. Diffusion models aren't new. You have seen them in systems like Delhi, where noise is gradually refined into a crisp image. What's new here is applying diffusion to text. Traditional large language models are autoregressive. They predict one token at a time, feeding each output back in to predict the next. It's like typing, left to right, token by token. A diffusion model works differently. It starts with noise and iteratively denoises it into a meaningful output. Now imagine doing that for text. You start from a random noisy sequence of tokens, which means some gibberish, and then you refine it into a coherent paragraph. You can see the effect visually in demos from the Mercury team. Early steps look like random text, and then words snap into place as the model denoises. I tried it myself, and it's fast. You can try it too in their public playground. This isn't a brand new architecture replacing everything. Mercury still uses the transformer. If you want a refresher on how transformers work, check out our video on Attention is All You Need. Think of the core as a transformer trained as a denoiser. At each refinement step, the model outputs a probability distribution over the entire clean sequence. But crucially, the final text isn't produced in a single jump. Instead, we iterate. Start from noise, take a small step towards clean, and then another and another until the sequence stabilizes into a polished paragraph. Here's the key difference from autoregression. Autoregressive models can only add one token at the end per step. Mercury's diffusion can adjust any token anywhere in the sequence at each step. And that's the source of its parallelism. Practically, Mercury operates on a fixed length canvas and learns to place the end of sequence, EOS, token at the right position. Early course steps might place blurry, word-like hints and a noisy guess at where the EOS should go. In later fine steps, the model refines both the words and the position of the EOS token, effectively deciding on the final length. The tokens after the now solidified EOS token are refined into padding. Once the iterative denoising process is complete, the final output is read from the beginning of the sequence up to the first generated EOS token. Let's clarify coherent text from random noise. The model always starts from noise, but the refinement steps are conditioned on your prompt. At step T, we don't just say, denoise this gibberish. The instruction is more like, given prompt P and the current noisy answer Z predict the clean final answer X. The model uses that prediction to take a small step to produce a slightly less noisy, still guided by P output. Repeat this enough times, and the random start morphs into a coherent prompt level paragraph. Because Mercury is trained and aligned on datasets that are similar to traditional LLMs, it inherits familiar prompting behaviors like zero shot, few shot, even chain of thought. From a user's perspective, it works like a drop in replacement. However, it's faster and more parallel. Now let's talk about the speed. Mercury models are designed to be extremely fast, delivering up to 10x speedups versus other high speed models. They hit rates that many thought would require custom chips. This matters most when you're building with coding assistants or doing vibe coding in a flow state. Long delays crush momentum. If you have ever felt, I could have typed this faster, that's the pain Mercury targets. And here are some numbers to anchor this. Mercury Coder Mini has been measured at around 1109 tokens per second, which is 8x faster than several leading open weight coding models, while still outperforming them on quality. Mercury Coder Small clocks in 3 to 10x faster than popular rivals like Claude 3.5 and Gemini 2.0 Flash, with comparable quality in benchmarks. In Copilot Arena, which is a community platform where developers rate AI coding assistants, Mercury Coder Mini is reported as the fastest model with an average response time of about 25 milliseconds, which is roughly 4x faster than GPT-4o Mini. And it's tied for second place in quality. In other words, speed without sacrificing performance. Having an ultra low latency changes the user experience. You can have coding assistants that complete functions before you lose your thought. You can have AI agents that can react faster and chain more steps within a time budget. Chain of thought and multi-turn reasoning, where long structured outputs land quickly, not slow in motion. Ultra low latency changes user experience. In summary, an autoregressive LLM writes one token at a time, where every token depends on everything before it. It's great for fine-grained control, but inherently sequential. Mercury, on the other hand, starts with a whole noisy paragraph. It refines all positions in parallel at each step. It decides the content and the length together by stabilizing tokens and the end of sequence position. It takes fewer serial steps, resulting in lower latency and higher throughput on modern hardware. Despite these differences, there are a few things that stay the same for you. Even though the engine under the hood is different, your workflow doesn't have to change. You can still do zero shot and few shot prompts. You can still nudge the model into reasoning traces when helpful. You can still get transformer quality representations, just delivered via iterative denoising rather than next token sampling. So that's a wrap. Thanks for joining us on AI Club Pro. Hit that subscribe button for more eye-opening AI stories and insights. Stay curious and keep exploring.